Unfortunately, this lecture is going to be a little bit difficult in this context because usually what I want to do here is kind of talk about walking around a room, and it kind of helps understand what's going on. Okay, in the previous lecture, what we looked at was functions of several variables. In particular, we're interested in functions that depend on two others. So I could write this as z to be a variable depending on two others. Now the graph of this function is of the form input, output. The input is comprised of two numbers and the output is 1. So if you plot input, output, it's two numbers and one number, it's three numbers. So the graph of this function is actually three-dimensional. Now I'm not really good at drawing these things. I don't think many people are. But I want you to think of it as a kind of a surface, so maybe some kind of a mountain or something like that. That's what the graph looks like. It's a three-dimensional surface. I want you to think kind of geometrically now. So we're thinking about these graphs, which are surfaces. Think of them kind of as hills and mountains. This is a perfectly good way of thinking about it because at each point you've input, output. The input you can think of as the latitude and longitude, and the output you can think of as the height above that point. So the surface of the Earth is a pretty good mental model for what these graphs look like. Okay. Now, imagine in this picture, so the orientation is a little bit messed up here in terms of the x's and the y's. What I can do possibly to make this picture here make a bit more sense is I turn this into a y and this into an x. So this is just, imagine this is a rotation of this. So we're going to have to use our geometric intuition as much as we can here. Okay, so what's going on here is, so we see that x is into the page, so that if you walk in this direction, this is what we're talking about. Now we put the axis here, so kind of imagine that if you look at the x-axis going into the page, just a little bit on the left, and what we're doing is we're walking up the mountain in this direction. Okay. And the question is, what's written, how does z change as I change x? Now you're walking in the x direction. So in this picture, you're walking up the mountain like this. We'll call this little point x0. And the question is, how does z change? Now z is just the height, so how does the height change? And this is the interesting thing as such. When you go in the x direction, your y coordinate does not change. And in fact, as I write here, I made a mistake because this shouldn't be an x0, because x is changing, this should be a y0. So y is fixed and x is changing. So y is fixed and you're walking along the x direction. And then you go down the back of it, which we can't see. So we're looking at the slope in the x direction is essentially what we're talking about. Now, to kind of imagine this, imagine that this is, say, north. Then this would be west. And when you walk directly north, you don't move in the east or west direction. Okay, we're getting a bit closer there. Although, okay, so I'm going to have to change this around just to be consistent with this. So change this to east and then this to north. So it's saying when you are headed in the east direction, there is no change in your north-south coordinate. Your y coordinate is fixed. Okay, this is what we're talking about here. Now what we're going to do is we're going to take this thing and look at it from side on, and you're just going to see something like this. And taken as a side view of the surface for y constant, z, the height, is a function of x alone. And if we're talking about rate of change or slope, as we were talking in the previous thing, as soon as you hear rate of change, as soon as you hear slope, you have to be thinking derivative. So what you're talking about here is what is the rate of change? So rate of change slash slope, same thing, remember. In the x direction, should be the derivative of the function with respect to x. Now there's a bit of a messing going on here, because I've said, okay, if you've got a specific fixed y coordinate, you can think of z as a function of x and b, and if b isn't changing, it's not really a variable, you're just looking at it as a function of x. So this is saying, okay, if you're talking about a specific path at a specific fixed y coordinate, if you want to find the slope or the rate of change, you just differentiate it as normal, no problem. So basically we're saying on these surfaces, if you walk in a specific direction, say in the x direction, it's no problem to calculate the rate of change. You just differentiate with respect to x. Okay. Now let's look at some examples. Okay. So, and these examples, by the way, we said in last week's lectures that when we're differentiating a constant times a function, we're going to get into the habit of fixing the constant and then differentiating the function. So I'm going to set this thing up like this. So I'm going to rewrite this thing. So we got a function of x and y. So imagine that the graph of this is some kind of a surface. What is the rate of change of z with respect to y when y is 2? So imagine this is 2. Well, I just want to find the rate of change. Now it'll depend on x, because say at x equal to 0 it'll be something, x equal to 1 it'll be something else. So when we do this, it'll be a function of x, and then if we're interested in a specific point, we substitute in the value of x to get the rate of change or the slope, same thing at that point. So we're imagining that now that this function of two variables, if you're fixing y equal to 2, really at a fixed y equal to 2, you just have a function of x. So we'll write this. So I'm going to rewrite this. So I'm going to write a z equal to x cubed is fine. Now what I'm going to do with x squared times y cubed, now they're both numbers. I mean, x is a coordinate, it's just a number. The order of multiplication doesn't matter. I'm going to put the y cubed first, and I'm going to write the y as 2 cubed. Now I'm not going to actually write it equal to 8, and we'll see why not soon. So y cubed times x squared minus twice 2 cubed. Okay, now we want to differentiate this with respect to x. Okay, so off we go. dz dx. Now it's a sum, so we're going to differentiate term by term, and differentiation is linear, which means we can fix constants. So the derivative of x cubed is you multiply by the power, reduce the power by 1, plus. Now differentiating 2 cubed x squared, 2 cubed is a constant, so I'm going to fix that constant. That's fixed, and then differentiate x squared. The derivative of x squared is 2x. And now what about minus 2 by 2 cubed? Well, that's just 16, it's just a constant. Now, if it's a constant multiplying by something, you fix it, but a constant on its own, you can fix it if you want, but then you're just going to be multiplying by the derivative of 1, which is 0. A constant on its own, the derivative is 0. So a derivative of 2 times 2 cubed is just equal to 0. And we can tidy that up if we want, but I'm quite happy for it to remain like that. So what we have is, if you want to differentiate or find the rate of change of z with respect to x and y is fixed, basically, I'm not sure what I'm going to write here, so it'll just be, it'll be dz dx, and maybe we'll say that, we can throw that out. So you're just going to differentiate with respect to x after substituting in y equal to b. Now what we're going to do instead, because here we're saying, oh, y is equal to 2 or y is equal to b. What you actually want to do is you don't actually want to specify what y is. You're going to say, oh, it's constant, but I don't want to say what it is necessarily. So you say, oh, I want to look at how the height changes when I go in this direction at all different values of y. Now, whatever, I don't have to specify the value of y, but once I do as such, I am not going to change y. So what you're talking about here is, rather than specifying the 2, rather than even specifying b, what we're going to do here is we're going to differentiate away. I'm not sure what I'm going to write, so it'll be the derivative with respect to x of f of x, and I'm just going to write y constant. So this thing is called the partial derivative, and what that means is it's looking at the rate of change of z with respect to x, but y is kept constant. So it's the rate of change in the x direction. So something like this. You do not, y is kept constant. You don't have to specify what y is, but it is constant. If it is a function of more variables, we'll probably talk about that a bit later. Okay, this is the partial derivative of f with respect to x, and you've also got the partial derivative of f with respect to y. So what that means is we have two first derivatives. We've got the slope in the x direction, and this is what we call the derivative with respect to x. But we also have the slope in the y direction, and when you go in the y direction, x is kept constant. So we have a slope in the x direction and a slope in the y direction. And the important thing about them is when you go in the x direction, y is constant. When you go in the y direction, x is constant. Now you do want to, well, in my opinion, it's good to understand that. You can probably do these questions without understanding that. I think you're better off though. Okay, so I think now we're going to look at a number of examples. Now what I'm going to do is I'm going to rewrite them every time. Okay, so say first of all I'm going to write f of x, y. This is, let me see, maybe let's get some space going. So differentiate respect to x and also y. So when you're going with respect to x, we're going to look at z as x squared plus, now y to the power of 5, if y is a constant, and you see if you're going with respect to x, y is a constant. So we're not saying it's 2, we're not saying it's b, it's just some constant. And a constant to the power of 5 is also a constant, so this is like y to the power of 5, some constant times x. Space is going to be tough here. Now in the next one, the constant is 6 is a constant, y is a constant, and x cubed is the thing that's changing. And then we also have plus, well, if y is constant, so is y to the 4. Now, it should be a little bit confusing why I wrote that, but what we're eventually going to do is we're going to say, okay, we're going to differentiate this function with respect to x and also y. When I'm differentiating with respect to x, only x is changing. Everything with y is constant. So when I'm going to differentiate this with respect to y, I'm going to see things slightly differently. With respect to y, so this means that I'm going in the y direction. X is a constant, only the y's are changing. So I'm writing red to represent the constants here. So x squared is constant if I change y, plus x here is a constant. I'm saying on the right hand side y is changing, so y to the 5 is a function, minus 6x cubed. This is going to be y changing, so x is constant, times y plus y to the 4. These are the same thing, but they're slightly different ways of looking at them. Okay, so what we write now is, now I can write partial, this funny symbol. It's just a maths thing, it's just called partial. And really what it's about is it says, okay, let the function change, but only the variable on the bottom is changing. Everything else is constant. Okay. So in particular, I'm going to calculate, say, partial z, partial x. I'm going to say only x is changing. So anything with y is constant. Now, let's differentiate. With respect to x, I have to be more specific. I can't just say differentiate this. It doesn't make sense. So, like if you're standing on a mountain, you say, what's the slope? It depends on what direction you're pointing. Same here. You can't just say differentiate. You have to say in what direction. Here I'm saying in the x direction. Now, differentiation with respect to x is differentiation is linear. So I can do term by term. If it's a sum, I can do term by term, fixing constants. So off we go. The derivative of x squared is 2x plus. Now I have a constant times x. If you're differentiating a constant times a function, we were saying before, you should fix the constant and then differentiate the function. What is the derivative of x with respect to x? Now, there's various different ways of getting at this, but if you think of x as x to the 1, the derivative of x to the 1 is 1x to the 0, and x to the 0 is 1. The derivative of x is 1. Minus. Now here you've got a constant times x cubed. Fix the constant 6y, and then differentiate the function x cubed. The derivative of x cubed is 3x squared. Plus, now, if y is a constant, so is y to the 4, and the derivative of a constant on its own is just 0. We can tidy that up if we want, sure we may as well. Get 2x plus y to the 5 times 1 is y to the 5, minus 6 by 3 is 18, x squared. Okay, no better. Right, so this is your, say you're at a point, say you're somewhere like here, that is the slope in that direction, the x direction. Now what about the slope in the y direction? So in the x direction, y is constant. Now in the y direction, x is constant, as we've kind of set up here. So we're looking at the derivative of z with respect to y. So with respect to y, x is a constant, so x squared is a constant. What's the derivative of a constant? 0. Plus a constant times a function of y. Fix the constant. What is the derivative of y to the power of 5? 5y to the 4. Minus a constant times y. Fix the constant, 6x cubed. And the derivative of y with respect to y is 1. Plus the derivative of y to the 4 is 4y cubed. And then we can tidy this up. Now here the order of multiplication doesn't matter, so I can do the 5 first, then the x, then the y to the 4. 6 cubed times 1 is minus 6 cubed, plus 4y cubed. Now the next thing is just saying there's loads of different notations for partial differentiation. I think mostly we're going to use this one, but we could have equally used partial f, partial x, and partial f, partial y. We used partial z, partial x. You can also use f1 and f2. f1 means differentiation with respect to the first variable, which is x, which is sometimes also written f sub x, which is not f of x, it's saying take the function, differentiate with respect to x, differentiate with respect to y. So this is basically it. It's just if you want to do a partial derivative with respect to x, differentiate as normal, but keep y fixed. So this is up the top there. Okay. So let's look at a little example here, and together with a little bit of the surface. Okay, so we've got a function f of xy equal to 4 minus x squared minus 2y squared. Find the partial derivatives at a particular point and interpret these numbers as slopes. Okay, so I think as before, I will write, actually this one's a bit easier, so I won't bother. So partial f, partial x. So if you're doing partial differentiation with respect to x, you're treating everything with y as a constant. And also it's linear, so you can do term by term, fixing constants. So differentiate this, minus differentiate this, minus differentiate this, you can fix the 2. 4 is a constant, derivative of constant is 0. Minus the derivative of x squared with respect to x is 2x. And now what I'm going to do here is, well, actually, I could fix the 2 if I wanted. But if really there's actually no function here with respect to x. So I might just write this down as a little note. This is constant with respect to x. What that means is if x changes, this doesn't change. And if y is constant, which it is if we're doing partial differentiation, this is just a constant. So this is a constant, and the derivative of a constant is 0. And now what we want to do is we want to evaluate this at the point we're interested in. Now, the point we're interested here is 1, 1. And so we just substitute x equal to 1 into this. Now y equal to 1, this isn't a function of y, so there's no point substituting it in. And you get minus 2 times 1, which is equal to minus 2. So that is the slope in the x direction at this particular point. Now it'll make a little bit more sense in a moment when we look at the picture. We can also calculate the partial derivative with respect to y. So again, you've got to differentiate term by term, fixing constants. So 4 is a constant, so its derivative is 0. With respect to y, x is not changing, so x squared is a constant, its derivative is 0. And now for differentiating minus 2y squared with respect to y, we'll fix minus 2. And y squared is a function of y, and the derivative of y squared with respect to y is 2y. So you end up with minus 4y, and we're interested, well, let's tidy it up first maybe, minus 4y. And we're interested in this at 1, 1. And if you substitute y equal to 1 into this, you get minus 4. Okay, so let's look at what's going on. So this is a little portion of the graph. I'm fairly sure this is the x-axis, and this is the y-axis. The point we're interested in is 1, 1, which is here. So it's 1 along the x, 1 along the y, and maybe we find the z coordinate. So put 1 in for x, 1 in for y, you get 4 minus 1 squared, 4 minus 1, minus twice 1 squared, minus twice 1, which is 2. So you get 4 minus 1 minus 2, which is 1. So the coordinates here are 1 along the x, 1 along the y, 1 along the z. Okay. Let's see how we're doing for time here, a little stuck. Okay, so what's going on? So the partial derivative with respect to x here means the slope in the x direction, which means basically the slope of this here. So this is, I'm going to write it like this, so this is kind of saying the rate of change in the x direction. Okay, that's right, the function is equal to minus 2. The slope is minus 2. Means as you go along 1, it goes down by 2 approximately. And all along this thing, the y coordinate is fixed. So this is all, we might also write y is equal to 1. Okay. And then we've got the other slope. Okay, it's saying interpreted as a slope. Maybe I should write instead of partial f, partial x. This slope is minus 2. It's the slope as x changes. And then the other slope is the slope in the direction of y. So I can just say maybe this slope is minus 4. And again, as you travel along that line, x is also a constant equal to 1. Now the next thing that's written down is that all stuff like product rule, quotient rule and chain rule, they also still apply. And we'll probably look at these examples in the next video.